Hey, welcome back to Combinatorics. In this video, we're going to start talking about the inclusion-exclusion principle. In particular, we'll prove this principle for the case of 2 sets and the case of 3 sets. Later on, we'll prove the principle in full generality for any number of sets. In this video, we'll also apply the principle to a few example problems, including some probability problems. In the last few videos, we've discussed probability, sets, and some basic operations on sets. These operations include unions, intersections, complements, and Cartesian products. In this video, like I said, we're going to talk about the inclusion-exclusion principle. This principle is a useful tool for determining the cardinalities of sets if we know the cardinalities of some other sets. We're going to start by proving the principle in the case that we have 2 sets. This proof will be pretty simple. And then we'll apply the principle for 2 sets to a few example problems. After that, we'll prove the principle for 3 sets, using a very similar method to the one that we used for 2 sets, just a little more complicated. Then we'll do some example problems with 3 sets. And like I said later on, we'll prove the inclusion-exclusion principle in full generality after we work on induction. So let's start out with the 2-set inclusion-exclusion principle. Suppose that we have 2 sets, A and B. Our goal is to find the cardinality of A union B in terms of the cardinalities of A, B, and A intersect B. So we're going to consider the elements of A union B. All of the elements in A union B are either elements of A intersect B, the complement of B and A, which we write as A minus B, or the complement of A and B, which we write as B minus A. In particular, we can say that A union B equals A intersect B union A minus B union B minus A. Moreover, we can observe easily that A intersect B, A minus B, and B minus A have no common elements. In other words, those 3 sets are pairwise disjoint. So, since we have a union of disjoint sets, we can conclude that the cardinality of A union B is equal to the cardinality of A intersect B plus the cardinality of A minus B plus the cardinality of B minus A. We also can observe that A is the union of A intersect B and A minus B. Moreover, similarly, B is the union of A intersect B and B minus A. So, this tells us that the cardinality of A is equal to the cardinality of A intersect B plus the cardinality of A minus B. And similarly, the cardinality of B is just the cardinality of A intersect B plus the cardinality of B minus A. Now, all we have to do is combine those 3 equations. And if we combine them together, we see that the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of A intersect B. And this is the 2-set inclusion-exclusion principle. So now we can use this principle that we just proved on some example problems. So for the first problem, let's consider a high school. And this high school has 100 students on the math team. There are 20 students on the computer team, and there are 105 students that are on math team or computer team. So here's the question. How many students are on both math team and computer team? So let's define some sets so that we can apply the two-set inclusion-exclusion principle. First, we'll let A be the set of students on math team, and we'll let B be the set of students on computer team. And let's see what the problem told us about A and B. Well, first, it told us that the cardinality of A is 100. The cardinality of B is 20. And the cardinality of A union B is 105. Now, all we have to do is plug these three numbers into the formula that we just proved for the two-set inclusion-exclusion principle. And we're trying to find the cardinality of A intersects B, which we see by using subtraction with that principle is equal to the cardinality of A plus the cardinality of B minus the cardinality of A union B. And that gives us 120 minus 105, which is 15. Let's look at another problem, but with the same setup. So we have the same school, still 100 students on the math team, 20 students on the computer team, and 105 students that are on math team or computer team. So the new question is how many students are on computer team but not on math team? So again, we'll let A be the students on math team, and B will be the students on computer team. What is this problem asking for? Well, it's asking for B minus A, specifically the cardinality of that. So we can look at the information that we have from the problem again. And again, we know that the cardinality of A is 100, the cardinality of B is 20, the cardinality of A union B is 105. And on the last slide, we saw that the cardinality of A intersects B is 15. So if we want to find the cardinality of B minus A, all we have to do is calculate the cardinality of B and subtract the cardinality of A intersects B. That gives us 20 minus 15, which leaves us with 5. And that is the number of students who are on computer team, but not on math team. Let's do one more problem with the setup. Same setup with the students on math team and computer team. But now the question is how many students are on math team, but not on computer team? So in the last problem, we found the cardinality of B minus A. Here, we just want to find the cardinality of A minus B. Again, A is the set of students on math team, and B is the set of students on computer team. Again, we have the exact same cardinalities of A, B, A union B, and A intersects B, 100, 20, 105, and 15 respectively. And similarly to the last one, we have that the cardinality of A minus B is equal to the cardinality of A minus the cardinality of A intersects B. So we get 100 minus 15, and this leaves us with 85. And that is the number of students who are on math team, but not on computer team. Now that we did a few examples with two sets, let's move on to the three-set inclusion-exclusion principle. For three sets, we'll name our sets A, B, and C. And our goal here is to find a formula for the cardinality of A union B union C in terms of the cardinalities of A, of B, of C, of A intersect B, of A intersect C, of B intersect C, and of A intersect B intersect C. We're going to try to use a similar method to what we did for the inclusion-exclusion principle in the two-set case. So we'll consider the elements of the union. And we can see that the elements of the union of A, B, and C are all either elements of A intersect B intersect C, or A intersect B minus C, or A intersect C minus B, or B intersect C minus A, or A minus B minus C, or B minus A minus C, or C minus A minus B. And those are all the possibilities. Moreover, all of those sets that I just listed, A intersect B intersect C, A intersect B minus C, and so on, all of those sets have no common elements. So they are pairwise disjoint. So again, like we did in the two-set inclusion-exclusion principle, we have a union of disjoint sets. So we can say that the cardinality of A union B union C is equal to the cardinality of A intersect B intersect C plus the cardinality of A intersect B minus C plus the cardinality of A intersect C minus B plus the cardinality of B intersect C minus A plus the cardinality of A minus B minus C plus the cardinality of B minus A minus C, and finally plus the cardinality of C minus A minus B. Now, in order to derive the formula for the three-set inclusion-exclusion principle, it's going to help us to find formulas for the cardinalities of A, of B, of C, and of A intersect B, of A intersect C, and B intersect C in terms of the 7 sets that we use in the sum for the cardinality of A union B union C. So first, let's start with the set A. The set A, we can write that set as the union of A intersect B and A minus B, which means that the cardinality of A is equal to the cardinality of A intersect B plus the cardinality of A minus B. That A intersect B, we can write that as the union of A intersect B intersect C and A intersect B minus C. The A minus B, we can write that as the union of A intersect C minus B and A minus B minus C. And that is how we were getting the sum for the cardinality of A in the bullet on this slide. So we can say that the cardinality of A is just the cardinality of A intersect B intersect C plus the cardinality of A intersect B minus C plus the cardinality of A intersect C minus B plus the cardinality of A minus B minus C. We can do something very similarly for B. B, we can write as the union of B intersect A and B minus A. B intersect A, we can write that as the union of B intersect A intersect C and B intersect A minus C. B minus A, we can write as the union of B intersect C minus A and B minus A minus C. This gives us that the cardinality of B is equal to the cardinality of A intersect B intersect C plus the cardinality of B intersect A minus C plus the cardinality of B intersect C minus A plus the cardinality of B minus A minus C. And One of those cardinalities I rewrote in the last line. All I did is I changed the order of the two sets in an intersection. I changed the B intersect A minus C to an A intersect B minus C because intersections are symmetric. And finally, we do something very similarly with C. We can write C as the union of A intersect C and C minus A. The A intersect C, we can write that as A intersect B intersect C union A intersect C minus B. The C minus A, we can write that as the union of C intersect B minus A and C minus A minus B. So we can write the cardinality of C as the sum of the cardinality of A intersect B intersect C plus the cardinality of A intersect C minus B plus the cardinality of B intersect C minus A, and finally plus the cardinality of C minus A minus B. We only have a few more cardinalities to calculate before we derive the final formula for the three-set inclusion-exclusion principle. The only ones remaining are the cardinalities of A intersect B and A intersect C and B intersect C. Here's the ones that we have so far. We got cardinalities for A union B union C, for A, for B, and for C. A intersect B is a little easier. This one we can write as the union of A intersect B intersect C and A intersect B minus C. And so we get the cardinality of A intersect B is equal to the cardinality of A intersect B intersect C plus the cardinality of A intersect B minus C. Similarly, we get that the cardinality of A intersect C is equal to the cardinality of A intersect B intersect C plus the cardinality of A intersect C minus B. And finally, the cardinality of B intersect C is equal to the cardinality of A intersect B intersect C plus the cardinality of B intersect C minus A. So we just found the 7 cardinalities that we were looking for. The cardinality of A union B union C, and the cardinalities of A, of B, of C, of A intersect B, of A intersect C, and of B intersect C. Now, all we're going to do is combine these together, all 7 equations that we found. And when we combine them, we see that the cardinality of A union B union C is equal to the cardinality of A plus the cardinality of B plus the cardinality of C minus the cardinality of A intersect B minus the cardinality of A intersect C minus the cardinality of B intersect C plus the cardinality of A intersect B intersect C. Now, how do we see that this equation is true? All you have to do is plug in on each side, for each of those cardinalities on each side, the values that we found in the equations for those cardinalities. So in other words, the other side of the equation, plug that in for each of those cardinalities. And you'll see that both sides become the right side of the equation that you see in the top bullet. The top bullet being the equation for the cardinality of A union B union C. The right side of that equation is what we get in the final bullet if we simplify both sides using the equations that we have for the cardinalities of A union B union C, of A, of B, of C, and of A intersect B, A intersect C, and B intersect C. So that last bullet is our 3-set inclusion-exclusion principle. And like I said, the inclusion-exclusion principle can be generalized to any number of sets. But before we discuss that, let's look at an example problem. So we're back to that high school, and just like last time, we have 100 students on math team, and we have 20 students on computer team, and we have 105 students on math team or computer team. But now we're talking about chess team too. We have 10 students on chess team. There are 3 students that are on both math team and chess team. And there are 5 students on both computer team and chess team. and there's one student on all three teams. Here's the first problem. How many students are on at least one of these three teams? Like last time, we'll define A to be the set of students on math team. B will be the set of students on computer team. And now C will be the set of students on chess team. From the problem statement, we see that the cardinality of A is 100, the cardinality of B is 20, the cardinality of C is 10, the cardinality of A union B is 105, the cardinality of A intersect C is 3, the cardinality of B intersect C is 5, and the cardinality of A intersect B intersect C is 1. We're trying to find the cardinality of A union B union C. In order to find that, we'd like to use the three-set inclusion-exclusion principle. We're only missing one piece of information that we need to use that principle. We just need to know the cardinality of A intersect B. But we actually found that in an earlier problem, which had the same setup. And we found that the cardinality of A intersect B is 15. And we used the two-set inclusion-exclusion principle to find that. Now that we have that piece of information, we can just plug in to the three-set inclusion-exclusion principle. And we get that the cardinality of A union B union C is equal to the cardinality of A plus the cardinality of B plus the cardinality of C minus the cardinality of A intersect B minus the cardinality of A intersect C minus the cardinality of B intersect C plus the cardinality of A intersect B intersect C. This gives us 100 plus 20 plus 10 for the cardinalities of A, of B, of C, and then minus 15, minus 3, minus 5 for the cardinalities of A intersect B, A intersect C, and B intersect C, and then a plus 1 for the cardinality of A intersect B intersect C. And this leaves us with 108. So the cardinality of the union of A, union B, union C is 108. In other words, there's 108 students who are on at least one of these three teams. Let's look at another problem with the same setup. So again, we have the 100 students on math team, 20 students on computer team, 105 students on math or computer team, 10 students on chess team, 3 students on math team and chess team, 5 students on computer team and chess team, and 1 student on all 3 teams. Here's the new question. How many students are on computer team or chess team, but not on math team? We'll define the same sets as before. A will be the set of students on math team. B will be the set of students on computer team. And C will be the set of students on chess team. The information we have from the problem is that the cardinality of A is 100, the cardinality of B is 20, the cardinality of C is 10, the cardinality of A union B is 105, the cardinality of A intersect C is 3, the cardinality of B intersect C is 5, and the cardinality of A intersect B intersect C is 1. And we found in the last problem and the earlier problem that the cardinality of A intersect B is 15, and the cardinality of the union of A, B, and C is 108. If we want to find the cardinality of B union C minus A, we can take the cardinality of B union C union A, and then we can subtract out the cardinality of A. This gives us 108 minus 100, which leaves us with 8. Here's a problem for you to do, and it's kind of similar to the last couple that we looked at. So same setup with the students on math team, computer team, and chess team. But the problem here is how many students are on computer team and chess team, but not on math team. So the last problem had an or, this problem has an and. And like I said, the inclusion-exclusion principle can be generalized to any number of sets. And we're going to prove this principle for any number of sets. But before we prove it, we're first going to discuss induction. And that's going to be in a later video. Before we get to the end of this video, let's briefly discuss what the inclusion-exclusion principle tells us about probabilities. And then we'll do another problem about poker. So we suppose that U is the universe of equally likely possible outcomes. And events A and B will just be subsets of U. By the two-set inclusion-exclusion principle, we can conclude that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. We can also write this in terms of events as propositions. So if we write our events as propositions R and S, we can say that the probability of R or S is equal to the probability of R plus the probability of S minus the probability of R and S. And like I said, we'll apply this to poker. So let's quickly review what happens in poker. We're talking about Texas Hold'em poker. So we're dealt 2 cards from a deck of 52 cards. This deck has 4 suits, clubs, spades, diamonds, and hearts. And each of those suits has 13 cards. 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace. Those are the 13. We won't worry about any of the other cards besides the 2 that you're dealt for this specific problem. We'll also ignore all of the bids, the blinds, the folds, the order of the cards, anything like that. All we care about here is just the cards that you're dealt. So the problem is to find the probability that you are dealt an ace or a king. So we'll define the universe of outcomes to be the possibilities for the cards that you're dealt. So we're dealt 2 cards. There's 52 cards total. So the universe of outcomes has cardinality equal to 52 choose 2. We'll define A as the set of these outcomes where we're dealt an ace. And we'll define B as a set of outcomes where we are dealt a king. We can count the number of outcomes in A. We see that this is 4 choose 2 plus 4 times 48. Let's discuss why that's true. So A is a set of outcomes where we are dealt an ace. For us to be dealt an ace, we're either dealt 2 aces or 1 ace. There's 4 choose 2 outcomes where we're dealt 2 aces because there's 4 total aces and we would be choosing 2 of them. There's 4 times 48 outcomes where we're dealt exactly 1 ace because there's 4 choices for the ace and 48 choices for the non-ace. So that's how we get the total number of outcomes for A. Similarly, we get 4 choose 2 plus 4 times 48 outcomes for B. There's 4 choose 2 outcomes for getting 2 kings, and there's 4 times 48 outcomes for getting exactly 1 king with a non-king. So we can say that the probability of A is actually the same as the probability of B because the cardinality of A is the same as the cardinality of B. So both of their probabilities are equal to 4 choose 2 plus 4 times 48, all of that over 52 choose 2. We simplify that, we get 33 over 221. Now, since we're applying the inclusion-exclusion principle and we're trying to find the probability of the union, we're going to look for the probability of the intersection. For the intersection, A intersection B, we see that there are only 4 times 4 outcomes. Because A intersect B, these are the outcomes where we are dealt both a king and an ace. There's 4 choices for the king, and there's 4 choices for the ace. 4 times 4 gives us 16 total outcomes in A intersect B. That means that the probability of A intersect B is 4 times 4 divided by 52 choose 2. This leaves us with 8 over 663. Now we're ready to apply the two-set inclusion-exclusion principle. So the probability that we want is the probability of A union B, which is equal to the probability of A plus the probability of B minus the probability of A intersect B. So we get 2 times 33 over 221 minus 8 over 663. That leaves us with 190 over 663. Before we finish this problem though, let's talk about another way to solve it that's much faster than the inclusion-exclusion principle, using another tool that we discussed pretty recently. So same problem, what's the probability that we are dealt an ace or a king? We'll define the same sets. A will be the set of outcomes where we are dealt an ace, and B is the set of outcomes where we are dealt a king. And the faster way to calculate the probability that we are looking for would be to use De Morgan's law. We're looking for the probability of A union B. This is equal to 1 minus the probability of A union B complement. Using De Morgan's law here, we can say that that's equal to 1 minus the probability of A complement intersect B complement. So we want to count the number of outcomes in A complement intersect B complement. We see that there are 44 choose 2 outcomes in A complement intersect B complement. Why is that? Well, there are 44 cards in the deck that are not aces or kings, and we're choosing 2 of those cards if we are in A complement intersect B complement. So, by definition, the probability of A complement intersect B complement is just 44 choose 2 over 52 choose 2, which implies that the probability of A union B is equal to 1 minus 44 choose 2 over 52 choose 2, and again we get 190 over 663. So we got the same answer 2 different ways, which is good. And here's another problem for you. What's the probability that you are dealt an even number card, like a 2, 4, 6, 8, or 10, or you are dealt a spade? Thanks very much for watching. See you next time.